So, 8086 architecture, so it consists of two units as we have noted in the last class. There is a bus interface unit and there is an execution unit. So, bus interface unit is on this right side. So, this actually containing the logic by which it can access the bus, that is address bus, data bus and all that. And on the left side you see that execution unit where the actual executions are taking place. So, we will look into this in detail. So, this bus interface unit, so to be more specific, so there are some 16-bit registers CS, DS, SS and ES. So, they are called segment registers. So, code segment register, data segment register, stack segment register and extra segment register. So, we will look into their functionalities shortly. And there is another 16-bit register which is the instruction pointer or IP. So, this IP is similar to this program counter that we have in 8085. So, here in 8086 this IP and this CS they too will be constituting the 20-bit address, okay, the address bus. Similarly, when it is accessing data, the DS or SS or ES along with that some other register may be combined and you will get the data address or the stack address like that. So, we will see that memory addresses are generated by a combination of this segment register and some offset. So, for program access, that is code access, so this CS and IP, so those two will be added. For others, some offset value will be added with the other segment registers. And there is a separate address generation ALU. Okay. So, this is one 20-bit adder and this adder is dedicated for this purpose. So, you see that if you look into this diagram, you see there is one ALU on the execution unit which also has the capability to do addition, but this ALU is not given the task of generating the addresses. So, for address generation, a separate address generation adder is put into this module. So, CS value and this IP value when they are coming, then that will be combined together to get 20-bit address and that 20-bit address will be put onto this address data on this address bus and through this bus control logic. So, it will be connecting to 8086 bus. So, this 8086 bus, you know that this is a multiplexed bus, 20-bit bus out of which 20 bits can constitute the address, 16 bits can constitute data and there are some status bits that will be multiplexed with higher order address lines to get 20 bits here. Okay. So, we will look into this one by one. So, this bus interface unit, the operation is like this. So, if this is a physical memory address, that is say physical memory starting at say 0000 to say 20000, so 4, so that way it is increasing. Now, so it is divided into segments. So, physical memory is divided into segments. So, maybe say 0 to 20000 hex. So, that is one segment. So, this is the next segment. So, we call this segments. Okay. Now, these segments may be continuous. So, segments may be disjoint, segments may be overlapping. So, this definition of segment is with respect to I should say the programmer. So, programmer may define the segments to be common, segments to be disjoint, segments to be overlapping like that, and the segment register settings can be controlled by which you can have a difference between this overlapping or this disjoint or that way. So, this overlapping pattern can be controlled by putting this segment register values. So, in this a particular program may consist of a number of segments like segment 0, segment 1, 2, 3, 4, out of which so this segment 0 and segment 1 they are continuous. So, after segment 0 segment 1 starts, segment 2 and segment 1 there is a partial overlapping. So, segment 1 also partially overlaps with segment 3, 2 and 3 are completely overlapped. So, then 3 and 4, 2 and 4 are disjoint. So, like that we can have different type of overlapping. So, total memory that 8086 supports is 1 megabyte. So, it is 20-bit address bus. So, total memory is 1 megabyte and it is divided into 64K segments. So, each segment has got a maximum size of 64K. So, 64 kilobyte. So, now you can think about different types of overlapping. So, it is not mandatory that your memory should be divided into 2 segment or 4 segment or 8 segment like that. So, depending upon the programmer's requirement it can be done, but each segment the size will be 64K irrespective of overlapping or non overlapping. And then there are 4 such segment registers CS, DS, ES and SS. So, it can use these 4 segments. So, if all the segments are distinct from each other, they are disjoint from each other, then this 64K multiplied by 4. So, you can get 256 kilobytes within 1 megabyte memory. So, there are 4 segments. So, this each segment is 64 kilobyte. So, I can have a total of 256 kilobyte of memory that can be addressable at one point of time. So, naturally there are other segments. So, out of this 1 megabyte only 256 kilobytes are accessible. So, rest are there. So, basically the purpose is that I can have a multi-processing system where different user programs are loaded in different parts of the memory. So, this provides a generic structure, like you can give 256 kilobytes to per user. So, you can support 4 users directly. So, that way, so that may be the simplest possible organization, and you can think about any other complex combination of these segment registers and the segment definitions. So, programs obtain access to code and data in the segments by changing the segment register content to point to the desired segment. What it means is that maybe I have in my program I have got say 2 data segments. So, this is one data segment and this is another data segment. So, at some point of time I want to access this data segment. So, in that case somehow this DS register should be made to point to the beginning of this. Sometime later in the program, so if you find that you need to access this data segment, so you can change the DS register so that it points to this data segment now. So, you see that at one point of time, so you can access 4 different segments by through these segment registers, but if you want, so you can change the content of those segment registers in the program. As a result, it can access different regions of the program, different regions of the memory during execution. So, the next is about the segment registers. We will start looking into more detail. So, there are 4 segment registers as I said. The first code segment register is CS, or it is called code segment register. So, this is a 16-bit register. So, this code segment register is basically for pointing to the segment of the memory that contains the code of the program. So, naturally the code is not modifiable. So, it is actually trying to distinguish between code program memory and data memory. So, in the sense that this program memory will be pointed to by this CS register, the code segment register, whereas this data memory will be pointed to by this data segment register, extra segment registers, like that. Of course, there are override options, like it is not mandatory that this code segment register cannot be used for data access. So, that can be done, but there should be some explicit overriding that way. So, if you do not take that overriding, then the code segment register is a 16-bit register. It contains the base or start of the current code segment. So, and IP, the instruction pointer, it will contain the distance or offset from the from this address to the next instruction byte to be fetched. So, if we say that okay, this is my memory, and in that memory, so my code segment is somewhere here. So, this is my code segment part, this is the code part. So, what it means that the CS register will point to the beginning of this segment, and within that at some point of time, if I am at this statement. So, this is this offset, this distance from the beginning of the segment, this distance is contained in the IP register. So, in after this access is over, so this IP will be updated, so that IP register will point to the next instruction, then it will point to the next instruction, that way. So, this CS colon IP, so it is normally written as a pair. So, CS colon IP. So, this CS colon IP, it contains the next instruction to be accessed. So, it is the next instruction to be accessed. So, that way you can say that the equivalent of this program counter that we have in 8085 is the CS colon IP pair. Okay. The CS colon IP pair. So, this will be converted into a 20-bit value. We will see how it is done. So, this bus interface unit. So, this will be converting this it will be getting this 20 bit physical address by logically shifting the content of CS register 4 bits to the left and adding the 16 bit contents of IP. So, we know that this CS register is 16 bit and this IP is also 16 bit. So, this is CS is 16 bit and IP is also 16 bit. So, first what it does is that the CS left shifted by 4 bit positions. So, you get this 20 bit pattern now. So, this is the 16 bit CS value that is that has been left shifted. So, we get another 4 bits which are all zeros. These bits are all 0, but overall number is now 20 bit. So, with that 16 bit IP will be added. So, 16 bit IP will be somewhere here. So, these bits will be taken as 0 and this is the 16 bit IP. So, that will be added and the resulting value will be 20 bit. This resulting value will be 20 bit and that is the physical address. Okay. So, this is 20 bit physical address will be formed by logically shifting the content of CS register by 4 bits and then adding the 16 bit IP with that. So, all instructions of a program, so they are relative to the content of this CS register multiplied by 16 and then the offset is provided by IP. So, this provides a very good facility for loading the program at different places. Like if at some point of time we find that the program can be loaded from memory location 1000, then this CS register can be initialized to say 1000 right shifted by 4 and then IP. So, that way it is while actually running the program. So, it will be the CS will be left shifted by 4 bits. So, so it will be doing fine. Whereas, so if it is, so what I mean is suppose this program is loaded from memory location starting at memory location 0 1 0 0 0, okay, that is a 20 bit address. So, program is starting from this address. So, for this purpose the CS register should be loaded with the pattern 0 1 0 0, okay. So, that whenever it is and the IP register is initially 0. So, that when the first instruction is being accessed, so this will be left shifted by 4 bits. So, as a result you will get the pattern 0 1 0 0 0, with that this IP value will be added. So, you get 0 1 0 0 0. So, it will be accessing this first location, then IP is incremented, it will be accessing the next location. So, that way it will go. So, this way we can have this 16 bit offset. So, program relocation can be done. So, program relocation is just changing the CS value, loading the program at different places. So, by just changing the CS value, the program relocation becomes simple. So, the next register segment register that we have is the data segment register. So, this data segment register is again or say DS. So, this is also called the register, this is also called the register DS. So, this DS register is a 16 bit register and it points to the current data segment. So, just like CS points to the code segment, DS points to the data segment and operands for most instructions are fetched from this segment. So, please note this term, it is the most instructions. Okay. So, you can, if you say that I want to get the content from memory location say 2. Okay. So, if I want to get the content of memory location 2. So, what will happen is actually when I say 2, this will actually mean DS colon 2, that is the content of DS will be left shifted by 4 bits, that is multiplied by 16 plus 2. So, whatever be the address. So, this DS, so when I say that I want to get the content from memory 2, so this is actually the location that will be accessed. So, DS into 16 plus 2. So, this way we can have this segment registers, there is a data segment register pointing to the data segment, and so most instructions means some instructions they use some other segment register for data access. That is for example, particularly when you are accessing stack, the stack segment register is SS is used for access, or whenever there is another segment register ES or extra segment register. So, that can also be used for data segment. So, this 16 bit content of the source index register SI and destination index register DI or a 16 bit displacement can be they are used as offset for computing the 20 bit physical address. So, DS, this SI and DI, so these registers we will find in the execution unit. So, if you say like say if you want to get into this register AX content of say DS colon SI. So, what happens is that this DS multiplied by 16, DS register multiplied by 16. So, that way it is giving me a 20 bit value. With that this SI register content will be added. So, you get a 20 bit address. So, 20 bit data address will be generated. So, that will be giving us the address for the data access. Similarly, the another register that can be used is the DI register, destination index, and also you can mention displacements in many other ways. So, when you look into the instructions, we will see that there are many other ways by which you can generate these offsets. Next, we have the stack segment register, which is commonly known as the SS register. This is the SS register. So, this is again the 16 bit register, it points to the current stack. So, as you can can understand that if I change the stack segment register, the SS register content, then it can point to different locations in the memory. So, as a result, it is not mandatory that in my memory there is only one stack. So, different user programs may have different stack segments, and they may be loaded, they may be accessed via the SS register in a different fashion. So, as and wherever you want to locate that stack segment, so you can load the SS register accordingly to go to that stack segment. So, it is a 16 bit register, it points to the current stack, and again the same thing, that the 20 bit physical address will be computed by this stack segment register plus the stack pointer SP for the push and pop instructions. Like you can have instructions in 8086 like this. So, you can have say instruction like push AX. So, what we want to do is we want to save the register AX into stack. So, to what address it will be pushed? So, that will be determined by the segment register content multiplied by 16 plus the stack pointer register. So, there is a stack pointer register available in the execution unit of the of this 8086. So, that value will be added with 16 into SS, and that will give me the address where the AX content will go. And there is another register which is known as the base pointer or BP. So, this is also used for some cases, some instructions in a particular addressing mode, which is called based addressing mode. So, there it will be using this stack segment plus this base pointer. So, in this case what will happen is, suppose I want to get the content of this location pointed to by SS colon BP. So, we can have instructions for that purpose. So, again the same thing, that is 16 into SS plus the BP. So, that particular memory location will be accessed and that content will be passed to AX. So, this is useful whenever you are using this stack for parameter passing type of applications. Like what happens is that, suppose I have got a procedure P1 and this procedure P1 has passed some parameters ABC to some procedure P2. So, it has got this ABC here, and in the code of P2, so we are trying to access this ABC. Suppose we are trying to get into the AX register, we want to get the value of A that we have passed. So, how to do this thing? So, you need to in case of 8085, we have seen that we have to explicitly use this push pop instructions to pop out the corresponding parameter from the stack and then do the operation. Here that is not necessary. So, here you can, in the stack segment we have got this ABCs, all these parameters that we have pushed, so that we have passed. So, they are in the stack segment register and for into the stack in the memory. Now, if the stack segment register SS points to the top of this, then the SS colon 0 is the A, then SS colon 1 is B, SS colon 2 is C, etc. So, you can initialize this BP, the base pointer, to say 1, and then you can say AX gets SS colon BP. So, what will happen? SS 1 means, so it will be accessing this B. So, as a result AX will be getting the value B. So, this can be done fine. So, we will see these techniques when the parameter passing is looked into, this based addressing mode is looked into. So, you see that the data access in this case is not by the data segment register, but by the stack segment register. So, Another register, another segment register has been provided, which is called extra segment register. So, this extra segment register, it is sometimes useful, because we may have instead of having a single data segment, we may have two data segments. So, if this is the memory, if this is the memory, so in the memory I may have two different data segments, and maybe this is one data segment. So, let us call it say data segment 1, and this is say another segment which we call data segment 2. Now, since we have got a single data segment register, so DS may be made to point to the beginning of this segment. Now, if you want to transfer some data from here to here, then how to do this thing? So, this is very difficult, because you see whenever you are accessing data, so it will be doing like DS colon offset. So, it will be doing like DS colon offset. So, within a single instruction you need to change this segment register value. So, that is not possible, because for changing this segment register value you have to first move some value to DS. So, one possibility may be that you move the content, or suppose I want to get the content of this location, copied to say this particular location in this new segment. So, one possibility is that you copy it to some code segment part, and then from the code segment you copy. In two steps we do this thing, but that will be difficult. So, instead of that, what facility that is provided is the DS, let DS point to this. So, you have got another segment register ES, which is pointing to this the other segment, that is why it is treated as an extra segment. So, this extra segment register is there, and again, so this is an extra segment in which another 64 kilobyte of memory can be accessed. So, the string instructions, so they have got this type of application, but in general I can say like say move AX comma say ES colon DI. So, we can have instructions like this. So, that way this EX the ES extra segment register multiplied by 16 plus DI, the content of that particular memory location will be coming to the AX register. So, this has got particular usage in the string instructions that we will see later, but otherwise also you can use this extra segment register. Then the instruction pointer register. So, this is a 16-bit register, it points to the next instruction to be executed within the currently executing code segment. So, at the beginning code segment register has been made to point to the beginning of that segment, and the IP register content is made 0. So, that in successive instructions, whenever one instruction has been fetched, this IP value is updated and CS value remains same. Okay, only the IP value is updated, so that it can go to the next instruction without affecting the CS register. So, this register contains the 16-bit offset address pointing to the next instruction code within this 64 kilobyte of code segment area, and its content is automatically incremented as the execution of the next instruction takes place. So, this is very much possible, this automatic incrementation. So, this is very much possible because you have got a dedicated adder in the bus interface unit. So, you can use that adder for doing this addition without affecting the ALU that we have in the execution unit. So, the next important component in this bus interface unit that we have is the instruction queue. As I said that there is a 6 byte instruction queue, and each of this location is 8 bit wide, and there are 6 such queues. So, you remember in case of 8085 we had one instruction register or IR, and I said that whenever the instruction is brought from memory into the CPU. So, this instruction is coming to the instruction register. So, here that has been taken one step further, like since the many a time what will happen is that this execution unit. So, this will be busy executing some instruction, and while it is executing the instruction it may not be using this bus, because it may be doing the register operations here. Maybe it is all the operands are in the register. So, that way it does not need to access the bus. So, this address this bus interface unit, instead of waiting for the current instruction to be over, so it can ask to get the next instructions next bytes of the program from the program memory. So, this is exactly what is done. So, in instruction queue the instructions are fetched and they are kept in a first in first out order. So, this is a first in first out queue in which, or the FIFO queue, in which the up to 6 bytes of instruction code are prefetched are fetched on the memory at a time ahead of time. So, as we will see that many of the instructions of this 8086 they can go up to 6 bytes. So, that is why this number 6 has been taken. So, that if the 6 bytes are fetched, that means at least definitely one complete instruction is available in the queue. Now, of course, there are instructions which are smaller than 6 bytes. So, that does not matter, but this it will always try to fill up this 6 byte queue. So, this is done in order to speed up the execution by overlapping the instruction fetch and execution. So, fetch and execute, so they are overlapping. So, when it is internally doing the execution part, so we can have this fetch part, the fetch part going on through this bus. So, this way we can have this instruction queue. So, this is the pipelining, because that we have shown previously that between the fetch, decode and execute stage there is a pipelining. So, here the pipelining has been taken a bit ahead, you can say, where this fetch is having 6 byte prefetch of these instructions from memory. So, next we will look into this execution unit part. In the execution unit, so the responsibility is to decode the instruction and execute it. So, there is a decoder in the execution unit, that is the control system. Okay. So, this control system, so this is the decoder. So, from this instruction queue it will get the successive bytes and it will go do this internal control system. So, it will be determining the control sequence, as we have seen in 8085 also at different clock steps the signals are to be generated. So, it will be doing that, it will be generating those internal signals for different clock cycles, and accordingly it will be activating these registers, this ALU and this bus, the content may be available on bus, etc., and that way it will be doing the operations. So, this 16-bit ALU has been provided. So, this ALU is 16-bit, whereas this adder that we have in bus interface unit, this is 20-bit. So, there is a difference, this is 16-bit and that one is 20-bit. So, this is 16-bit ALU for performing this arithmetic and logic operations. Then this there are registers, we have got general purpose registers AX, BX, CX and DX. So, these registers are 16-bit registers and they can also be thought about to be consisting of 8-bit pairs, like AX can be divided into 2 registers AH and AL of 8-bit each. BX can be thought about 2 8-bit registers BH and BL. So, they can be accessed either as 16-bit register or 2 8-bit registers. And there are some more 16-bit registers, the stack pointer SP, the base pointer BP and the index registers SI and DI. So, SI stands for source index and DI stands for destination index. So, this SI and DI instructions, they are very much used for string manipulation and this block transfer of data. So, some of this is, as I said, that some of these 16-bit registers can be accessed as 2 8-bit pairs that we have seen. And this SIDI, so this is source index, destination index. So, they are also useful for transferring the content of a portion of memory to some other portion, the multi-byte data movement. So, that for that purpose also this SIDI are utilized.